I'm Colton Krosick, and I'll be doing Exam 1, Part 2 of Dr. Carlos Coe's Transport 1 class, UC. And this is where I'll be finding the max angular velocity before a mess occurs, assuming we have a cylindrical container, the initial height of the liquid equals the radius of the cup, and we know that the fluid will eventually rise at some angular velocity of omega to the top of the cup. And so here what we have is kind of the shape of the cup, of a cross-sectional of it, and we have here the radius you can see is equal to the initial height, and this is the total height of the container, which is big H. And then here's with what we see with angular velocity of omega, and we can see here that we have a parabola here at the top of the water going to the edge, and this is what we'll be trying to solve for, this omega. And then we'll start here with the change in pressure over the change of the radius, small r. We'll get into that in a second. Small r can be anything from here to here. And it can change. It's anything in between what is the big R, and we have is equal to rho, which is the density, times omega squared times the little radius, and then we can change this around to get dP equals the density times the angular velocity squared, and then we want to put integrals here from 0 to the radius, p, 0 to p, and this one here we have 0 r, radius r dr, and make these prime here to differentiate, and then we can solve for that, and we get p equals omega times rho, which is the density, angular velocity times the density times little radius squared over 2. And then to kind of give a better visual of what we're doing here, we have a parabola, and we have here this, and what we can have here inside is, this is little h, and from the point at which h is to the center is little r. And then this is still h, but this is, we're going to call this d, and yeah. So then to solve for little h, and then this of course can be little h be needed. R would then extend from here to there. Call that R1, R2, H1, R2, H2. So we get h equals angular velocity squared times radius squared over 2 times gravity, and then we show that h of little r, when little r is equal to big R, equals angular velocity squared times radius over 2 times gravity, 9.8 meters per second squared. Don't quote me on that. That's not important. That's not what we're solving here. And then we can show that because we know that this is really pressurized here is equal to this. It's not so pressurized. So volume of this is that's volume. And then you can go and say that pi radius, pi r squared times little d is equal to the volume of this. That's disproportionate. Here. And then we want to integrate this. And that's going to help us get our answer. First we say that radius, the big radius minus distance plus h r radius is equal to real radius. That is equal to h. And then say that the change in volume is equal to h2 pi r dr. V is equal to dV, which is equal to 2 pi volume liquid 0 h r dr, and you can simplify that. It gets pi r squared equals omega squared pi r squared over 4g. And then you can solve for that and get d equals omega squared r squared over 4g. And then bring it down here, r minus, this is the equation we used to solve, r minus big R minus little d plus h of r, little r equals big R is going to equal h. So then you can plug in for d, plug d into that, and we should have our little HR equation, which will give us r minus omega squared r squared over 4 times g plus omega squared r squared over 2g. And then we want to isolate the h and the r, we put those on one side. H minus r is equal to omega squared times r over 4g, and then you want to isolate those again, so we want to isolate the omega now, and we get omega squared equals 4g h minus r over r squared, and then take the square root of these, and we get omega equals 2 square root of g h minus r over r, and that is our max angular velocity.